I love this class. You guys are the best. All right, so yeah, you know, some things feel arbitrary about this, and the truth is, yes, things are arbitrary. But you know, in life, a lot of things are arbitrary, and we've just kind of accepted them. So, one of the arbitrary things is the significance level. Okay? The significance level, which we call alpha. Okay? This is the point at which we decide when a p-value is large or small. Okay? And so if the p-value is greater than alpha, we say it's large. We say the p-value is large. And when the p-value is large, what is the conclusion we make?
We do not reject.
We do not reject the null hypothesis. Okay? And we do not have evidence to reject the null. We do not have evidence to support the alternative. You know, all of those things. Everything that goes along with we do not reject the null happens when the p-value is greater than alpha. Okay? So all of those other things, you know. Do not have evidence. Do I have to write all of these out? Do not have evidence to reject 0, blah, blah, blah. No evidence to support the alternative, etc., etc. Okay? So everything that goes along with not rejecting the null, that goes along with when the p-value is greater than alpha. Okay? On the other hand, if the p-value is less than alpha, we reject the null. And everything that goes along with that. We have evidence, etc., etc. Evidence to support the alternative, to reject the null, all of those things. Okay? Those all go with when the p-value is less than alpha, okay? Somehow, the most common alpha, commonly selected alpha, is 0.05. If your p-value is less than 0.05, you reject the null. If your p-value is greater than 0.05, you do not reject the null. But you can technically choose any value of alpha, and they would be equally valid. And these are just arbitrary lines, right? So in the United States, we say you have to be 21 in order to drink alcohol. In Canada, it's 19, okay? So people have chosen different, quote, lines in terms of age at which someone is deemed responsible enough to go drinking. And is one more or less valid than the other? No, okay? So we can select any value for alpha. Okay, so other common choices are alpha equal to 10%, alpha equal to 1%, alpha 2%, or you know, any other value of alpha we want, okay? Technically valid. But what does it mean to have a large alpha or small alpha? Well, okay, so alpha is the probability of what we call a type 1 error. In hypothesis tests, there's two types of errors we can make, and we gave them the most creative names of type 1 error and type 2 error. Okay, we'll talk about type 2 error in a moment here. So a type 1 error, this is, type 1 error is the mistake where you have rejected the null hypothesis, but the null hypothesis is actually true. So maybe we go to 8th grade, okay? And we look at the heights of boys and girls. So maybe you've come to the conclusion, you rejected the null hypothesis that, whatever, 7th grade or 8th grade, that the boys and girls, the average height of boys and girls in 8th grade are different. You've rejected that, you've rejected the idea that they're the same, and you've concluded that they're different. But in reality, if somehow we were to gather all of the data, what if it turned out that their mean heights were actually the same? That would be a type 1 error, okay? So let's say, let's say we go to 7th grade, and we look at, heights of boys versus girls, okay? And let's say our p-value turns out to be equal to 0.04, okay? And let's say our alpha is 0.05. So here, what's our conclusion? Whatever the data it is, okay, our conclusion is we reject the null hypothesis, right? And we conclude that the heights of boys and girls are different, or that the mean heights of boys and girls are different. Okay. Do you remember all of the other gibberish that I wrote up here?
0.8436.
No. I mean, in terms of our conclusion. I would say something like the p-value is small. The p-value is 0.04, which is small enough for me to kind of ignore the possibility that this happened by random chance, right? But technically, there's still a 4% chance that the data I observed happened by random chance, right? So I said 4% is small enough where I can ignore the possibility that it happened by random chance. But it turns out maybe I was wrong to do that. Maybe the data that I observed actually was a result of random chance, okay? And there's a 4% probability, and in fact, there's a 5% probability that I would end up at alpha or something smaller. right? So there's a 5% chance that I would reject the null hypothesis, but the null hypothesis is actually true. There's a 5% chance that the data I observe is weird enough to lead me to the conclusion to reject the null hypothesis, even though the data itself was just a result of random chance. Does that make sense? Okay. So there is always an alpha probability that our data is quote-unquote weird enough to lead us to reject the null hypothesis, even though data resulted from random chance. Okay. So alpha is the probability of a type 1 error, and a type 1 error is where we have rejected the null, but the null hypothesis was actually true. Okay, and that happens, and it happens just by random chance, right? Just like when we took confidence intervals and we made 95% confidence intervals, sometimes the data we gathered was odd enough where the confidence interval we produced didn't actually get the true parameter that we're looking for. Same idea. Okay. The other thing is a type 2 error. Okay, so type 1 error is the mistake where we have rejected the null, but the null is actually true. What do you think a type 2 error is?
The opposite. We don't reject it, but we should.
Yeah. The type 2 error is we did not reject the null, or someone might incorrectly say that we accepted the null, but we never accepted the null. We did not reject the null, but the null hypothesis is false and should have been rejected. And the probability of a type 2 error, okay, alpha is the probability of a type 1 error. What do you think the probability of a type 2 error is?
1 minus alpha. Beta?
Alpha is the first letter of the alphabet.
Beta?
Beta is the second letter of the alphabet, so we would go with beta. 1, alpha. 2, beta. Alpha, beta. Alphabets. Okay. So our type 2 error is beta. Okay. And we have something called power, which is equal to 1 minus beta. Alright, so 1 minus, whenever you have the probability is 1 minus something, that would be the what? Complement, okay. So power is the complement of type 2 error. So what is the complement of type 2 error?
Alpha?
Not committing type 2 error, okay. So what is not committing a type 2 error? So just put a big not in front of this sentence, right?
We did not reject it, but it is not false.
No. You gotta put not in front of the whole thing. So that would be,
We did not.
we do reject it, or we not reject it. So we do reject the the null hypothesis when the null hypothesis is false. Okay. That's power, or the probability that we do reject the null when the null hypothesis is false. So how good are we at detecting when the null hypothesis is wrong? That's the power of the test. Okay, so power is a good thing. So if we want to increase our power, right? What are ways we can increase our power?
Lessen the p-value.
I'm sorry?
Lessen the range of the. Put it closer to our alpha. Does that make sense? I think I'm saying this incorrectly, but.
I'm not sure. I'm not quite sure what you mean. Well, okay. Well, maybe these are not good questions to ask. So.
Make beta smaller?
Okay, well, how can we make beta smaller? Okay, so the truth is we generally don't have a whole lot of choice about beta, okay? Beta usually results. We generally don't get to pick beta. Okay. But we can pick alpha, okay? So what happens when we increase alpha?
It allows for more error.
Less requirements for
Less significance.
Yeah, okay, so if we increase alpha, alright? If we increase alpha, what happens? Okay, so alpha, maybe let's say we started off alpha at 5%. Let's say I increased alpha to 10%. Okay, that means I'm going to be rejecting the null hypothesis more or less often. So if alpha goes from 5% to 10%, so alpha equal to 5% goes to alpha equal to 10%, will I be rejecting or more often or less often?
Rejecting it more.
I will be rejecting it more often, right? Because before my p-value had to be less than 5% for me to reject it. Now if my p-value is less than 10%, I'm going to reject it, okay? So here I'm going to reject the null hypothesis more often. Okay? So if I reject it more often, I'm going to not reject it less often, which by the very nature that I'm not rejecting it less often, that decreases my chance of beta. I know it's like tongue twister and mind trap, right? But because I'm rejecting it more often, I'm less likely to commit the mistake of not rejecting it when it's wrong. Okay? So I'm rejecting it more often, so I'm less likely to commit this mistake, right? So I am less likely to commit type 2 error, so that increases beta. I'm sorry, that increases power. I'm sorry?
Oh, no. Doesn't that mean you also increase the
it means
that you commit type 1?
Yeah. Because I'm increasing alpha, I'm directly increasing my probability of a type 1 error. Okay? But the side effect, or the downside, increasing probability of type 1 error.
So increasing the probability of the type 1 error is also increasing power?
In general, yes. So increasing type 1 error will also increase power. Okay? so for example, let's say you went to the doctor, and I don't, you know, they do some kind of screening, right? Cancer screening. So they do something. So they could. So what would and the results from the test are either positive or negative. Okay, so what would a type 1 error be? So if you go to the doctor, right, the null hypothesis would be you have you're healthy, no issues, and the alternative is that something's wrong.
They detect that something's actually wrong.
Yeah. Okay. So
when
let's
it's not.
just say doctor visit. Okay. So type 1 error, not type 1. Null hypothesis is you are healthy, or have no problems, and the alternative, something is wrong. Okay. So you go through the test, and the test can either flag you as problems or no problems, right? Reject the null or don't reject the null. Okay, so ideally, if you are healthy, we don't reject the null. And if something is wrong, we reject the alternative. I mean, we reject the null and we conclude the alternative. Okay? We would call a false positive would that be a type 1 or type 2 error?
2.
Well, what does it mean? False positive means
That you get positive. You get a positive, but it shouldn't be. So like.
okay. Well, I guess what does so is positive when you go through the test and the results come back positive? Is that a good thing or a bad thing?
Bad thing.
That means you've got something's wrong with you, right?
The other way around.
So false positive would be a type 1 error. Okay. And a false negative would be a type 2 error. Okay. So if we make the the test super sensitive, right? It's like you sneeze, it's going to say, oh, something's wrong with you. Okay. If we make it super sensitive, we're going to increase false positives. Like, a bunch of people will be flagged with false positives. Okay, so we're increasing our type 1 error, but we're decreasing our type 2 error. Okay, by the very nature of that. All right. So on the other hand, if we decrease alpha, all of the opposite things happen. Okay, so we're more likely to commit type 2 error. But we are less likely to commit type 1 error. So your choice of alpha essentially depends on whether you prefer to make a type 1 or type 2 error. So with a disease screening, would we rather have false positives or false negatives?
False positive.
Okay. So in general, we'd rather catch someone who might potentially have the disease and be wrong about that than to tell a bunch of people that they're healthy when something's wrong, right? I mean, this is especially critical for something like HIV, right? If we would much rather have false positives than false negatives, because if we tell someone they don't have HIV but they actually do, they might spread the virus, and that would be a problem. Okay, false positive, that's like nobody wants to receive that news that they might have the virus. But then we could do further tests and conclusively decide whether or not someone has that. So for something like an HIV test, where we'd rather make type 1 error than type 2, would we pick a large alpha or small alpha? Large alpha, right? Okay, so if a type 1 error is preferred over type 2 error, okay, take a large alpha. So examples of that. An HIV test. Okay. Fire alarm or smoke detector. What does it mean to have type 1 error for a smoke detector?
Really sensitive.
False alarm, right? It means the alarm goes off, but there's not really actually any fire. Okay. A type 2 error would be there is a fire, but it didn't trigger the alarm. Okay, and that's bad. Okay, that's no good. Okay. We'd rather be inconvenienced by a false alarm than than to be ignorant of a real danger. Okay. On the other hand, can you think of any situations where type 2 error is preferred over type 1 error? Okay. So if a type 2 error, so again, no, we don't want to be making errors, okay? But if we were forced to choose one error over the other, this is how we decide whether we want large or small alpha. So type 2 error is preferred, okay? And again, type 1, we pick a small alpha. Yes.
Would you want it, for that one, would you want that in, like, if you were assessing research, so you'd want a smaller, so you'd want, like, 0.05, because then in that case, that would be a higher significance of that being
I would
reliable.
say it depends on your research. It depends on your research.
Because
Okay.
is that kind of related to, like, how journals pick what gets published or not, depending on, like, how, to what value they
it
give that?
depends on the journal, and there's a lot of criticism about journals today. Kind of this 0.05 gold standard has, I don't know. So I don't know. That's a can of worms. Okay. Okay. So here, this is an example that I can think of. Okay. Is a criminal case. Okay. What does it mean to commit a type 1 error for a criminal case? Well, first off, what is our null hypothesis and our alternative hypothesis?
You're not guilty.
Yeah. So null hypothesis is defendant is innocent. And the alternative is that the defendant is guilty. Okay. And it's okay that I'm writing innocent for the null hypothesis, okay? Because these are the hypotheses. The conclusions that the jury makes is to either reject or not reject the null, but it's never to accept the null, right? Okay, so in a criminal case, the defendant is innocent is our null, and the alternative is that the defendant is guilty. So what does it mean to commit a type 1 error?
So, the defendant is guilty.
Yeah, so an innocent person is convicted. So type 1, innocent person is convicted. And type 2 would be,
Guilty person is set free.
yeah, a guilty person goes free. Okay, and this always, I don't know, brings up a little bit of debate, or some people might disagree. But at least, we are taught, and the way our founders decided to set up our justice system is they said a type 1 error is far worse than a type 2 error, right? Someone, who said that? Matthew Henry or something said, I would far rather see 10 guilty people go free than to see one innocent person behind bars. Or something along those lines. I don't know my history. But, so in that case, we pick a small alpha. Okay? And they actually say this if you go to court, or at least on court dramas. They say pick a small alpha, but they don't say pick a small alpha. What do they say?
If you have any doubt.
They say, before you convict, you have to make sure you are convinced beyond a reasonable doubt, right? They say that phrase, beyond a reasonable doubt, which means make sure, basically use a small alpha. Make sure your p-value of the data is very small, okay, beyond a reasonable doubt, so that before you convict, okay. And that's really the defense's most powerful weapon, I think, in terms of proceedings. If they can bring forth just a reasonable doubt, you're supposed to acquit. You're supposed to acquit. And then, whenever there's a high-profile case and the defendant is found not guilty, it always, causes people to get upset. But the way our legal system is set up, that's how it goes. Okay. So, depending on your situation, you're probably not dealing with criminal cases when you're dealing with statistics here, but if you can decide between one type of error or over another, okay, that might guide your choice of alpha. Okay. Otherwise, if you don't know what to do, just pick alpha equal to 0.05. That seems to be the quote safe choice. But if somebody else chooses a different alpha, that goes. Okay. Let me talk about how t-tests. So all of these hypothesis tests that we've done so far, they've all been called t-tests because we use the t-distribution. But and their t-tests are highly related to confidence intervals. Okay. When we looked at a confidence interval, how did we make a decision as to whether or not there was a difference between the respective population means?
Whether there's a 0 in it or not?
Yeah. So the conclusion from a confidence interval was if 0 is in the interval for mu1 minus mu2, we do not have evidence of a difference between mu1 and mu2. Okay. Now imagine we took the same data that we used for a confidence interval and we ran a t-test or a hypothesis test. If we came to the conclusion that there is no evidence of a difference, what conclusion should we make for our t-test using the same data?
That the null is not rejected?
Yeah, we should make the same conclusion. We should make the same conclusion if we're using the same data. The conclusion that we come to with a confidence interval should be the same conclusion we come to with a t-test, which would be that we do not reject the null. Okay, so if we use the same data, here's the connection. If our confidence level is 95%, okay, this corresponds to a t-test. This corresponds, I should say, to a two-sided t-test, meaning, or non-directional t-test, meaning we have a not equal sign in the alternative. This corresponds to a two-sided t-test where alpha equals 0.05. Okay, 95% corresponds to 5%. If our confidence interval is 99%, this corresponds to a t-test where alpha is 0.01. Okay. So anytime we have a alpha, level alpha, this corresponds to a confidence interval with 1 minus alpha percent confidence. Okay? And so this is where we kind of saw that when we used the computer and we did the t-test on the computer. I think on the example on the computer, I think our p-value is equal to 0.045 or something like that. Okay? And so when I made a 95% confidence interval, the 95% confidence interval did not contain 0. Okay? Because this corresponds to equivalent to using alpha equal to 0.05, right? And in both of these cases, my p-value is less than alpha, so I would conclude evidence of a difference, and therefore, using a 95% confidence interval, I would also conclude evidence of a difference. Okay? So both of these would conclude to evidence of a difference. On the other hand, if I did a 96% confidence interval, did contain 0. And this is equivalent to using alpha equal to 0.04. Okay? And so my p-value here is greater than alpha. And so the conclusions from either confidence interval containing 0 or p-value greater than alpha is no evidence of a difference, right? So our conclusions depend heavily on our choice of alpha or our confidence level, but they work together here. Okay, we have our brain wrapped around that. Let's try some brain twisters then. Or problems that you might see on next week's quiz. So let's say you perform a t-test, perform a two-sided t-test with alpha equal to 0.05. Your conclusion is do not reject the null hypothesis. If we did the same exact test with alpha equal to 0.10, what would our conclusion be?
Still don't reject it.
If we did the same exact test with alpha equal to 0.01, what would our conclusion be? Would we conclude if I made a 99% confidence interval, would it contain 0? What about 95% confidence?
Us? Yeah.
Alright. Do we have answers here? Answer here is don't know. The answer here is do not reject. The answer here is no. And the answer here is no. Okay? So, if we perform a two-sided t-test with alpha equal to 0.05, what does that and our conclusion is to not reject the null hypothesis. What does that say about our p-value?
It's greater than 0.05.
Yeah, our p-value, I don't know exactly what it is, but I do know for sure it's bigger than 0.05, okay? So it could be 0.07, it could be 0.20, it could be anything, as long as it's bigger than 0.05. So if we did the same test with alpha equal to 0.10, what would our conclusion be? We don't know, okay? Because it's bigger than 0.05, so it might be less than 0.10, but it could be bigger than 0.10. We don't know. But if alpha was 1%, what would we conclude? We would conclude the same, okay? Because if it's bigger than 0.05, it's definitely bigger than 0.01, so we would not reject. Alright, if we made a 99% confidence interval, would it contain 0? No, okay? Number 2, in number 2 it says we concluded not to reject the null hypothesis. Oh, I'm sorry. The answer to both of these is yes. I apologize, I made a mistake. Okay, so here I concluded not to reject. So my 99% confidence interval, I would also conclude not to reject, which means it contains 0, okay? Because I have no evidence of a difference. Sorry, I made a mistake there. Okay, and then for a 95% confidence interval, same conclusion, because at 5%, I found that there was no evidence of a difference. So if I make a 95% confidence interval, I should find no evidence of a difference. So that means it contains 0. Is that all right? Okay. Sorry for the mistake. Okay. All right. So the last bit here, okay, is we're gonna take a small jump and do some stuff in chapter 8. Okay. This is our last bit, and then we'll be done. Chapter 8, section 2. This is the paired t-test. Okay. So all of the tests that we've done in chapter 7 assume that the two groups of data are independent. Our two groups of data are independent, so we're dealing with boys. They are selected independently of the girls that we selected. Or we selected rats that were exposed to toluene. They are independent of the rats in the control group. Okay? The two groups are independent. With a paired t-test, our two groups of data are not independent. Okay. So here, there's some natural pairing between the two groups of data. So maybe you're dealing with husbands and wives, okay? Probably the most common example of paired data is before and after, okay? You're dealing with the same group of individuals, and you have a before measurement, they do something, and you have an after measurement, okay? So common examples. Is before versus after, okay? Or you might have, husbands and wives, or any type of partnership or pairing, whatever they might be, okay? Partnerships, pairs, studies of twins, okay? People, for a while, people loved doing studies on twins because they were trying to eliminate genetic factors and stuff, okay? And the thing is when you're dealing with a paired t-test, you cannot treat them as independent data. If you did, you might come to the wrong conclusion, okay? So do not treat paired data they were independent. Okay, so here is, it's a silly example, but I think it illustrates our point. Alright, so let's say some company markets a weight loss pill. Okay, so they say, you know, guaranteed to work, okay? You take the pill, you're gonna lose some weight. Alright, so someone says, okay, well let's see if this works. Does it work? Alright, so let's say in our, we have a before. And, okay, so let's say we have, you know, Adam, Bob, Chuck, Daryl, whatever, okay. Howell, Isaac, okay, we'll keep going. Alright, so let's say this is, we've got 7 people here. Alright, so let's say Adam weighed 230 pounds, Bob weighed 165, Chuck weighed 240, and Daryl weighed 150, Ed weighed 180, Frank 195, and Gary 50. Okay, sure. This is too much data. Let's just get rid of Gary. Sorry, Gary. Okay, and then after they take this pill, let's say we have this. 6, 7, 8, 9, 10. Let me punch this into the computer, and let me get mean before. And then standard deviation before. Mean after. Standard deviation after. Okay, so the mean here is 193.33, and the standard deviation is 35.73. And the mean after is 189.67. And the standard deviation after is we could do a t-test, right? We can do this, and we know how to do a t-test as if we treated these independently, okay? So this is the wrong way to do it. The wrong way would be mu1 minus mu2 equals 0, and the alternative, well, here we are hoping that the weight loss pill works, right? So what would our alternative be? Mu1 minus mu2 is greater than, less than?
Greater than.
It's greater than 0, right? Our before should be more than our after. Okay? And we can do this, and I'll just have R do it for me. Okay? And it tells me that my test statistic is 0.1788. So after I do all of this, my test statistic is 0.1788, and my p-value is equal to 0.8617. All right. So our conclusion here would be do not reject the null hypothesis, right? And so that means we do not have evidence, what? That the weight loss pill works.
But wouldn't you just look at the beginning thing when you look at the means?
I'm sorry?
Wouldn't you just look at the means and see that there is something before doing that?
Oh, okay, yeah. I'm supposed to check the directionality, right? So I mean, if I check directionality, and indeed, 193.33 minus 189.67 is indeed positive. Okay, that is.
So then, wouldn't you reject it?
I mean, it is greater than 0. Okay.
Right.
It is greater than 0, so I continue with the test. Okay. But my p-value ends up being large, so I do not reject the null hypothesis. Okay. But this is the wrong way to do it. Okay. Because here, my conclusion would be we do not have evidence that the weight loss pill works. But if you look at the people and their individual weights, does it seem like the weight loss pill is working? Yeah, everybody who took the pill lost some weight. Maybe not drastic amounts, but a couple pounds, 3 pounds. Everybody who took the pill lost some weight. So it does seem like it works. Okay? So the problem here is that by treating the groups independently, the difference caused by the weight loss pill, which is pretty small, okay, maybe only about 3 or 3.5 pounds-ish, okay, the average difference caused by the weight loss pill is lost, okay, or is clouded by the fact that the original starting weights of the people is so diverse, okay? Because the original weights of everybody was so diverse, or the standard deviation here was so big that to detect a difference of 3.5 pounds overall, that seems insignificant, okay? But if I focus on just the difference themselves, then it becomes clear that the weight loss pill actually works. So whenever you're dealing with paired data, the correct way to do it, okay, is you make a difference column. Okay. And if you don't make the difference column, you're going to be in trouble. So here my difference is 5 pounds. This person lost 2 pounds. This person lost 4. This person lost 5. This person lost 2. And this person lost 4 pounds. Okay, so everybody lost some weight. And the question is, dealing with with paired data, the correct null hypothesis is that the mean difference is equal to 0, and that the alternative is that the mean difference, okay, that the mean of the difference column. So I no longer have two mu's. I only have one mu, and it's the mean of the difference column. And here, for the directionality check, okay, I want the mean difference to be greater than 0. Okay? Because I want the people before weight to be more than their after weight. So I want do I have evidence that the difference from before minus after, is that greater than 0? So that's what I have going on here. Okay? And so here I get my sample difference, d bar. Okay. Okay, so my the mean of the difference is 3.67, and the standard deviation of the difference is 1.366. Okay. And so here, my test statistic is what I observed. I observed a difference of 3.67, and I subtract off the mean, what I'm expecting, of 0, and my standard error in this case is going to be s over the square root of n. Simple enough, right? So here I've got 6 people, so I'm going to do 1.366 over the square root of 6. So I have 3.67 over 0.558. And I get 6.58 for a t-test. 6.57. My test statistic is this. Okay. So now I'm going to look this up in my t-table. How many degrees of freedom do I have?
5.
5 degrees of freedom, okay? Because it's no longer n1 plus n2 minus 2. I'm only dealing with one column, so I'm only dealing with the difference column. So once I've established the difference column, I can ignore this. And so I have 5 degrees of freedom. Degrees of freedom is n minus 1. So I have 5 degrees of freedom, and I look this up in the t-table. And for 5 degrees of freedom, 6.58 is bigger than my last number.
No, it's not.
It's not? 5 degrees of freedom? Oh, it's not. You're right. It's just a little bit smaller. So my p-value is going to be in between 0.005 and 0.0005. Okay, so looking at 5 degrees of freedom, I have 0.005 and 0.0005. And 6.58 is in between there. So my p-value, whatever it is, less than 0.005, but bigger than 0.0005. My numbers: 4.03 and 6.869. So, someone has asked me, why do I put the 0.0005 over here and the 0.005 over here? This is just, I guess, habit of learning math, that smaller numbers go to the left and bigger numbers go to the right in general. So that's why I do it that way. But it's perfectly valid and not wrong to write it this way. Okay? And this is also equally valid and correct. So my p-values between 5 10,000ths and 5 1,000ths. So I reject the null, and I conclude that the weight loss pill works. Okay.
And is the reason that you're not doubling the t values to get the p values because you check the directionality?
Yeah, because I've got a greater than sign, I'm not doubling it. Okay? The only time I double it is if this has a not equal to. Okay? Okay.